Hello everyone. Namaste. Good morning, good afternoon, and good evening. Well, it's late evening here in Nepal, and we are here back again with brand new episode of webinar on geoscience for sustainable development. This is Suraj Gautam, a civil engineer and a disaster risk reduction and management professional from Institute of Himalayan Risk Reduction. First of all, I would like to welcome you all in our Himalayan webinar series. Well, Institute of Himalayan Risk Reduction is an organization established with a vision to prepare risk-informed societies for disaster resilience and sustainable development. So, to contribute onto this, IHRR has been regularly organizing Himalayan webinar series on geoscience for sustainable development and disaster risk reduction and management. So far, we have successfully organized 7 episodes of webinar on geoscience for sustainable development. And yes, it's the turn for the 8th one. And today we'll be having interesting topic on using Convergence Research to connect 3D architecture of the Himalayan thrust wedge to the seismic hazard and risks in Western Nepal, which will be presented by Professor Dr. Michael Murphy, Professor Dr. Michael H. Taylor, Dr. Sin Bemes, Dr. Richard Styron, and Dr. Elaina Sutley. So on behalf of the organizing team, we are really grateful to all our presenters who will be sharing us with their insights and healthy experiences. So it is indeed an honor to welcome our presenter, Dr. Michael Murphy,
who is professor at Department of Earth and Atmospheric Sciences, University of Houston, USA.
Professor Dr. Michael S. Taylor, who is professor at Department of Geology, University of Kansas. Dr. Sin Bemis, who is working as research scientist at Virginia Tech, USA. Dr. Richard Styron, who is working as active fault specialist at Global Earthquake Model Foundation. And Dr. Elaina Sutley, who is chair council assistant professor in structural engineering at the University of Kansas. So to make this session more interactive and lively, we have Assistant Professor Dr. Basantaraj Adhikari from Institute of Engineering, Tribhuvan University as our session moderator. And Dr. Adhikari is also the visiting scientist at Institute of Himalayan Risk Reduction. So we'd like to welcome all of our participants and all our regular attendees who are joining us through our social media live streaming and also through this Zoom platform. And talking about the webinar, this webinar event has also been featured in the website of Relief Wave and Prevention Wave. And talking about the webinar registrations, so far we have around 211 registrations from different parts of the globe. So to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction, and we'll be receiving the queries and feedbacks from our social media live streaming as well as from our Zoom chat box. So we have been organizing this webinar series on a regular basis, and we believe this webinar series has been supporting our early career scientists, DRR professionals, academicians, and all the participants. And yes, it's a beginning and we'll go a long way ahead. So before starting our session for today, I would like to have a short introduction about Institute of Himalayan Risk Reduction. IHRR is a research institute established with an objective to assess and understand the risks to contribute for the sustainability. And our team constitutes of professionals with expertise and experiences in the field of disaster risk reduction, in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So we have a vision of preparing risk-informed societies for disaster resilience and sustainable development, and we'll be prioritizing and training and mobilizing DRRM professionals and promoting DRRM solutions through science, engineering, technology, and innovations. So we have our 4 thematic areas. First of all, we also work on the disaster risk reduction and management consulting works. And we do work on research and development. And we also have a concept of disaster academy. And another one is the youth in disaster risk reduction and management. So far, we have been organizing a number of projects. Like we have been involved in the number of projects that includes recently we had a collaborations, and under the collaborative approaches, we developed a national platform for the COVID-19 information dissemination, which was endorsed by the Ministry of Health and Population. Besides, utilizing this lockdown period, we carried out some UAV surveying of the urban core, dense urban settlements. And we have actually carried out the survey of around 120 square kilometer and the work is still going on. So we have been utilizing this lockdown period, and we have also published our voluntary commitment in the Sendai voluntary commitment, as we can also see there. Besides, we have been regularly organizing our Himalayan webinar series. And so here we are today. And now I would like to share some house rules for today's webinar. The audio and video of the participants shall be switched off. The overall session of the webinar will be recorded. For any queries, the participants can write up in the chat box or in the comment section of Facebook streaming live. And the waiting room has been enabled, and only the registered users with their original identity will be allowed to enter the webinar room. And also, I would like to request our participants to rename and keep their name as mentioned in the registered link. I would also like to request our participants to strictly avoid using the annotations. Annotations during the presentation shall be taken offensive, and the participant will be removed from the webinar. And the feedback links will be provided during the session, and we'll be providing the participation certificates as well. So without any delay, I would now like to move on with our session, and may I request Dr. Basantaraj Adhikari to proceed further with his moderation. Thank you for now. Dr. Basanta?
Can you hear me now?
Yeah, it's audible. Yeah.
Thank you, Suraj, for your wonderful introduction about Institute of Himalayan Risk Reduction. Welcome everybody this beautiful evening here in Nepal, and morning there in US, and different time zones in different part of the globe. Today we have interesting webinar on neotectonics and seismic hazards in the Western Nepal. And then we have requested our colleagues from US to give a talk. Actually, it's a project that we are doing in Nepal for more than 2 years. I think 1 year is still, we'll have 1 year more time. And so we'll have Professor Mike Murphy, Michael Taylor, Sin Bemis, Richard Staren, and Elaina Sutley, and then the team member constitutes of myself and Deepak Chamlagai also. And then so they will give a presentation, and we'll address your questions and comment at the Q&A session after the presentation. So I'll introduce our eminent speaker today. So the first is Professor Dr. Michael Murphy. He's a professor at Department of Earth and Atmospheric Sciences, University of Houston, USA. He completed his PhD from University of California back in 2000, and his research mostly focused on origin, development, and structural evolution of the continental crust, which is fundamental process of operating in the continental crust, is driven by his deep interest in and the challenges of unraveling the structures of Earth in complexly deformed regions. So currently he's working on two processes that have and continue to shape the history of the Earth: intercontinental collision and continental breakup. And he has published research on upliftment of Tibetan Plateau and role of extensional fault system during the orogenesis. And the next, our colleague presenter for today, Professor Dr. Michael S. Taylor, is a professor of geology at University of Kansas, USA, and he completed a PhD in geology from University of California in 2004. And his research interest lie in the studying active fault system, orogenesis, and development of continental orogenic plateaus using remote sensing, geodesy, isotope geochemistry, and structural geology to understand the dynamics of continental deformation. So he teaches structural geology, field camp, advanced mapping, and neotectonics. He has published research on remote sensing and neotectonics of the Tibetan Plateau, Andes, and the Himalayas, so most of the important regions around the globe. And he specializes in the role of active fault system during the mountain building process. And another colleague today we have Dr. Sin Bemis. He is from Department of Geoscience, Virginia Tech, USA. He's completed his PhD in geological science from University of Oregon in 2010. And his research mostly lies on the field of earthquake geology and neotectonics, integrating structural geology, geomorphology, quaternary geology, and geochronology to investigate the process controlling the earthquake recurrences, fault system evolution, and mountain growth. And he uses paleoseismology and neotectonics models to understand the evolution and seismic hazards of complex transpersonal fault system, including the Denial Fault in Alaska and the San Andreas Fault in California. And then another colleague today we have Dr. Richard Stein from ZEM Foundation, Los Gatos, USA. He's an active fault specialist in ZEM Foundation and research affiliates of the University of Kansas. He's completed his PhD from University of Kansas in geology in 2012. He's specialized in fault mapping, slip rate estimation, and how tectonics and earthquake processes influences seismic hazard. His research mostly interests lie in active tectonics and seismic hazard, seismic computing, and innovation in quantitative geoscience. And another colleague today, Dr. Elaina J. Sutley. She is a Chair Council Assistant Professor in Structural Engineering at University of Kansas. She specializes in interdisciplinary resiliences studies, resiliences research at the nexus of human disasters and the built environment, with more than 60 associated publications. She completed her PhD in civil engineering from Colorado State University, and mostly research focus on performance-based seismic design, social vulnerability, hazard mitigation, and structural reliability, optimization techniques and decision-making system, design resilience communities, large-scale dynamic testing and monitoring, advanced material, infrastructure rehabilitation using composite material, shape, memory, alloys, light frame or system. So we have very good colleagues and esteemed colleague that we are working for a long time. And these esteemed professor and researcher, geoscientists, structural engineer, earthquake engineer are working for a long time in the Himalaya and Tibetan Plateau, not only that region, but mostly other part of the globe. But today, so we are going to learn and hear their presentation on using convergence research to connect the three-dimensional architecture of the Himalayan thrust wedge to the seismic hazard and risks in Western Nepal. So the floor is yours. I would like to invite to start your presentation. Please proceed, Mike.
Control of this. Yeah. All right. Let me make sure I see my connections to move forward and back. All right. Well, thank you, everybody, and good evening. I want to thank everybody for joining this webinar. I want to for sure thank the Institute of Hazard, Risk, and Reduction, as well as Basanta for inviting us to come and share our most recent work. We're sort of in the beginning stages of the project. We've had one field season, but over the next 2 years, we're going to be coming to Nepal, conducting field work, and really looking forward to collaborating. In fact, what we want to do next year and the year after that is to offer and deliver short courses on topics you'll see in this webinar, as well as methods. So if you see anything that's interesting, we'll be working with Deepak Shamlagain and Basanta Rajadhikari to host these short courses. So keep in touch with them. I think they'll, we'll try to get that going for next year. Let me see if I can get these things moving. Let's see. Andrew, can you go to the next one? All right. Well, our project is sort of focused on activities to address two main questions regarding sort of the seismic hazard and neotectonics in the Himalaya. And that is, what is the role of splay faults in the Himalayan megathrust models? What controls lateral segmentation of rupture zones and hence magnitude? Now in this webinar, a few of us are going to tag team these topics. I'll first start off by walking you through the 3D architecture that Soya Fan and I have been aiming to get a better control of in Western Nepal. And then I'm going to hand it over to Andrew Hoxie from Kansas, who's going to highlight our neotectonic efforts that he's been working on with Mike Taylor. And then we're going to transition to some seismic hazard and risk. Richard Styron will present the work that he and Elaina Sutley have been working on. Next one. So let me introduce you to the team. It's a great team. We really enjoy working together. You might recognize some of these last names and some recent publications, but we all have different skills, have certainly enjoyed working together. But let me highlight the students, because the students are the ones that do a lot of the main work. And so I want to introduce you first to Soya Fan over here. He's one of my students at Houston, done some great work on the 3D architecture. There's Andrew Hoxie, as you'll hear from him later today, on neotectonics from Kansas. Alok Bhakta from Nepal, who's now at Kansas. And Michael Vadman, who's also working on the paleoseismology of the area. Next one. So this is the team. Here's our playing field. It's a great place. It's very special for many of us. It's significant because it hosts the largest and highest elevations in the globe. Has an average elevation of greater than 4,500 meters, much taller than anything on the United States or in North America, or in most of the lower 48 of North America. It drives the heat that it radiates. It's so high. The heat that it radiates drives atmospheric circulation. It's also the source for the largest submarine fans on the planet, and it's bordered by the largest human populations. And this is significant because it is a storehouse of energy that drives great earthquakes and landslides along its southern margin here in the Himalayas. Next one. So that southern margin geology is shown here in the Himalayas. I know you've had several talks about, great talks about the geology and architecture of the Himalayan thrust wedge by, I think, first Alex Webb. Mary Hubbard did a great talk on the sort of the central eastern Himalaya. And then I think you saw Rhoda Korosi the other day give a really neat talk on how the complexity of the different faults are within that wedge. Next one. So when you look at two cross sections, here's two cross sections across the Himalaya, one by Webb and others in 2011, and then one I published in 2007. And what you should notice is that there's a lot of difference, even over the short distance. You can see a great difference in the colors of the blue and the pink along strike. And so it's this geology that we really want to explore. Next one. Now, I think we all sort of are familiar with this sort of celebrity status that the Himalayas have. At least, for those of us that teach Geology 101, every year we break open our textbook. This is sort of the basic figure that thousands, hundreds of thousands of geology students look at to sort of see what the final stage of the Wilson cycle looks like when we've closed an ocean basin, therefore creating a suture zone. We realize now through studies in the Himalayas that this region is tremendously thickened by a system of thrust faults that root into a mega thrust at the bottom. And what these diagrams show is that we often have this sort of linear mountain belt in which convergence is perpendicular between the two plates. Next one. But you know, when you look at all convergent plate boundaries globally, none of them are straight. They're always curved. You know, this might be an extreme example in Southeast Asia, but almost all convergent plates are curved. So you sort of ask yourself, what should we expect beyond that model that I showed you before? And so back in, let's see, in 1972, it was Fitch who started off a series of papers that was noting features or fault systems that form in these oblique convergent margins. Later on, in beautiful detail by Bob McCaffrey in his 2009 Earth Science Review paper, sort of it described how that oblique convergence gets accommodated by a sliver splay fault and a megathrust to form something we call a four-arc sliver. This four-arc sliver is translated along strike due to the oblique convergence. In 2015, Silver and others in the Himalayas sort of noted this system of faults that extends down from southwest that obliquely crosses the origin and intersects the main frontal thrust down here by a little town called Tonson. And they interpret, along with some geodynamic modeling by David Whipp, suggested this area would behave like a four-arc sliver with this splay fault right here acting as the rear margin. So that system is shown here, the next one. So this is what the basic seismotectonic framework of that splay fault looks like. Back in 2014, Matt Cannon and I interpret that splay fault to root and soul with the megathrust. Here we call it's known as the main Himalayan thrust, sort of links with it right here. And combined with other studies on the brittle plastic transition and elastic coupling along the megathrust, suggests that it forms right at the boundary between a rheology in which the down dip portion aseismically creeps or promotes aseismic creep, while the up dip portion stays locked over some nominal seismic cycle and results in, when it becomes unlocked and moved, results in these great earthquakes. Now, when you look at microseismicity, like a map here published by John Harvey and others in 2014 in Lithos, you can see that there's two belts of microseismicity that develop in Western Nepal. In Eastern Nepal, in Central Nepal, it's very straightforward. Nice one big lineament of microseismicity suggesting one large ramp. But once you come over into Western Nepal, you can see it bifurcates to two belts, one in the north and one in the south. And so that northern one, we think, correlates to the position of the splay fault, suggesting, you know, based on many sort of seismic models for the Himalayas, suggests that there's a ramp there that's building up concentration of stress, resulting in a lot of small little earthquakes going off. And so because of this, Soya Fan and I were like, man, we better really try to understand the deeper structure. We think there's a deep control on the position of this Western Nepal fault system. And so next slide. And so what we did was we took this sort of pseudo 2D approach to get a 3D, to create this 3D geologic model. This is mostly it was just published by Soya in this earlier this year. What he did was he compiled and made about 25 cross sections extending all the way from the Northwest Himalaya into the Central Himalaya over here. All of this work was done using a couple programs, ArcGIS as well as MOVE, structural software by former company Midland Valley. And so what we're interested in, next slide, is to look at the total thickness. Our first goal with this model was to look at changes in the thickness of the thrust wedge along strike. So what you're looking at is the thickness of that thrust wedge that you've heard about in several other webinars. And this represents the thickness between the South Tibetan detachment at the top and the main Himalayan or mega thrust at the bottom. And there's sort of a couple observations you can note here. You can sort of see that the front in blue is a very thin part of the wedge, while the hinterland has is super thick. It's thicker in the central part, like you can see here, all in the reds, the warm colors, and it gets tremendously thinner to the west in this area we call the Zada Basin, not too far adjacent to this other massif called Leopardgil. And so many people, you know, a popular model to explain these thickened regions in the hinterland that I've published on, Alex Webb, On Yin, several people have published on this idea that we have these crustal scale duplexes potentially rooted at the floor by the main Himalayan thrust that are accommodating this tremendous thickness. And so there's two key elements to this duplex model that I'll talk to you about. Is that duplexes, we'll see, we sort of model them with having a frontal thrust or a frontal ramp that evolves at the front of the thickened region and then bordered along its margins by these lateral ramps. You can sort of see where we're going to put that duplex here in this cross section way back in this super thick hinterland region. Next slide. Next one. And next one. This is just to show you a few of the different maps. I encourage you to go to Fan and Murphy 2020 to take a look at that. So assuming this duplex model to explain those patterns in the thickness of the hinterland results in this ramp system that's described in more detail in the GSA bulletin by Soya. But what the key part here is we have a series of frontal ramps, as you can see here in gray. There's 3 structural levels of flats going from deep in the north, and you're looking sort of to the south. So this is the north side over here. We have a series of these mid-crustal frontal ramps that are bordering the very front of the duplexes, and they terminate laterally along these lateral ramps. Because this is just a snapshot, duplexes evolve by incorporating or by propagating a new thrust at the front and creating a new ramp. So with time, each of these frontal ramps migrate southwards and the lateral ramps also extend southwards. So this is an evolving system. This is sort of a snapshot in time during sort of a mid evolution. These 2 cross sections here show you what the shape of the hanging wall looks like over here. And what I want to point out now is this mid-crustal ramp here in gray that comes across, and I want to note its disruption along strike and its termination into these lateral ramps. This is important to us because what we're interested in understanding now is what the surface deformation looks like above this hypothesized ramp system. And what we're going to talk about, and I'm going to hand this over to Andrew in just a second, is this blue line. This blue line represents this semi-continuous active fault system we've been working on, which we call the Western Nepal fault system. And I think with that, I'll let Andrew Hoxie from Kansas take over to describe what we've accomplished over the last year and highlighting even some other things.
Okay, thank you, Mike, and thank you all for the opportunity to speak today. So as Mike was saying, we're looking at towards the south in this view. If we turn that around and we look at the map of the region now, here the West Nepal fault system strikes northwest southeast from approximately the southern reach of the Karakoram down to the main frontal thrust somewhere near Tanzan. The system is composed of northwest striking right slit faults and north striking extensional faults. And as you can see along the length of the system, the kinematics and the strike of these faults varies along strike. And they're segmented similarly to our understanding of the mid-crustal ramp. And so we interpret these faults as acting in tandem to one another, creating a splay fault that branches with the main Himalayan thrust, effectively forming a hypothesized 4-arc sliver that consists northwest translation of the region shown in pink, as Mike described earlier. If that's true, then there's an increased probability of all these segments rupturing simultaneously, which would result in a large magnitude earthquake and impact the entire region. So in order to test this hypothesis, we need to have a better understanding of the slip history of these faults, and particularly the quaternary slip history. So this work is really resting on a foundation of some earlier work from the 1980s by HETAUDA and others. And they basically identified and described a whole series of active faults in the high Himalaya. And the way that they did that was by primarily looking at satellite imagery and looking for topographic features that are offset and deformed by the active structures. And so in this image, what you're seeing is a whole series of streams and topographic ridges that are truncated and offset, and they all show offset consistent with right slip along this particular fault. And so what we want to do is add spatial resolution to these existing maps and also add geochronology so that we can determine slip rates on each one of these segments independently. We'll then be able to evaluate the temporal variation by comparing to, say, geodetic data or geologic offsets. And then we'll also be able to evaluate each segment independently and understand how well kinematically linked they are. A strong kinematic link would imply that there's strong slip partitioning, and that has important implications for the probability of a large magnitude earthquake. So in the spring of 2019, we focused on the central portion of the fault system. We flew into Jumla and then with the help of our guide service, hiked down to Jafal. And along the way, we saw numerous examples of active faulting. So here we can see a fault scarp. It's approximately 1.5 meters tall. We also saw truncated and offset topographic ridges. And then in this image, you can see a house down here for scale. And if you look up from there, you can see there are a whole series of channels that are, again, truncated and offset, all with offset consistent with right slip motion. We also made more detailed maps of a couple sites, and I'm going to focus on the one that we made of our Talphi site. So this is a field image that's looking towards the southwest. What you can see on here are two streams that are flowing from right to left, and they straddle this alluvial fan that the slope gradient is down to the left. And that slope gradient gets completely interrupted by this fault scarp here. It measures approximately 40 meters tall, so it's a really large fault scarp. And then if you follow the strike of that fault laterally, you can see that there's water basically being dammed by the activity on the fault, creating this large ponding surface. So we mapped that out in greater detail, and we identified 4 unique fluvial terraces. And I also want to point out this one terrace in particular, this T4 terrace riser, which intersects the fault at a near perpendicular angle. And that's particularly useful because we'll be able to use this as a geologic marker. So here's the map that we actually produced of that region. This blue arrow is showing approximately the location of that photo. Again, this T4 riser here intersects the fault at a near perpendicular angle. And it's most likely that this T4 riser was produced by this stream that's farther to the east. And so if we use that as our marker in our reconstruction, when we reconstruct the map, then it measures approximately 389 meters of right slip offset. Like I said, we also want to add a component of geochronology to this so that we can determine a slip rate. So we also collected samples here. Here's Dr. Mike Taylor and one of our guides, Ita, and they're collecting a sample for optically stimulated luminescence. Okay, we also spent a fair amount of time at the Tibrikot site. And even in the satellite image, the evidence for active faulting is quite compelling at this particular site. There are a series of channels here that all flow from northeast to southwest, and they're all deflected right where they intersect the trace of the fault. Along the trace of the fault, you can also see these spectacular shutter ridges, again, all showing a right slip deformation. I'm going to show a photo now that's basically where this green arrow is. Again, we're looking towards the southeast, and you can see these shutter ridges in the distance. The fault strikes right down through here. And Michael Vodwin and Sean Bemis were particularly fortunate at this site because they had a fresh exposure of the fault to look at. And so what we see here is a well-defined shear zone that separates young, late Holocene agricultural sediments from a highly fractured bedrock. And this relationship is overlain by new agricultural terraces, suggesting these terraces were reestablished after the earthquake that created the juxtaposition. So this site further demonstrates the useful activity of this fault system and suggests that this fault was definitely active recently. As we continue this work, we're going to be moving south. And so I just want to show one example of our planned sites. We're calling this site the Dogari Pond site. And so you can see here a small pond here on the left, and it has this very linear shoreline to it. If you follow that linear trace up, then you'll see that there are these set of topographic ridges that are clearly truncated and offset. And so our interpretation is that this is a sag pond associated with this active fault. And you can see there's also an associated fault scarp. It's north facing and it's approximately 6 meters tall. We mapped this out in greater detail using the remote sensing data. So this blue arrow here is approximately where that photo was taken from. What you're looking at here is a map of basically different glacial moraines. And again, they're all truncated and offset with a right slip sense of motion. So as we continue this research, we're really asking one central question, and that is like, how are all of these segments and these different faults connected kinematically? Like we said, we'll be able to evaluate each one independently, and we'll be able to determine the probability that these faults could rupture all simultaneously. We interpret that this system forms a branch line with the MHT near Tenzin, and that would mean that if the MHT and all of these segments are linked kinematically, then the rupture could propagate through the whole system. So we know this area is seismically active, but a rupture of that size would produce intense shaking for the people that live there, and particularly some of the population centers nearby. So I think I'll leave it at that. And for more on the seismic hazard, I'm going to turn it over to Richard Styron.
Okay, thank you, Andrew. So again, as Andrew did a great job of describing, the connectivity of the different faults in the Western Nepal fault system is expected to have a significant control on the seismic hazard and risk of the region. So we have, here on the screen, we have 3 different hypotheses for fault connectivity and how they relate to different geodynamic scenarios that could cause the Western Nepal fault system to be active in the current tectonic regime, as well as different structural styles of connectivity of the faults. So on the farthest left, we have a strong slip partitioning hypothesis where all of the faults in the Western Nepal fault system, so 300-ish kilometers of strike slip and oblique slip faults are all connected and capable of simultaneous rupture. And this ends up being a fairly large event in the high magnitude 7s at least, and can expose a pretty large fragment of the Nepali population to strong ground shaking. So that's Mercalli magnitude 8+, including the town of Pokhara here. Some of the more intermediate hypotheses involve weak slip partitioning and thrust-related faulting. And so these are tectonic scenarios that would cause the Western Nepal fault system to be active, but not capable of producing large coordinated slip on all of these different faults in the form of very large individual earthquakes. And so these different scenarios produce much less exposure of the populations to very strong ground shaking. But this is, these are hypotheses that were developed fairly early on. As our work progresses, we'll be able to refine them more. And we're starting to use more sophisticated modeling of probabilistic seismic hazard and risk in order to come up with better estimates of how individual buildings can respond to the wide variety of earthquakes that are possible in this scenario. So the work that I'm presenting now is a mix of preliminary work that I'm doing, as well as work by our colleagues Elaina Sutley, who is a structural engineer and has been working a lot on the building surveys and modeling. Okay, can I change the slides? I cannot. Okay. So first I'll talk about the probabilistic seismic hazard analysis. So we're at a very preliminary stage of this, and we're making a fault-based model for the main Himalayan thrust and the Western Nepal fault system. Most of the previous existing probabilistic seismic hazard analysis, or PSHA models for Nepal, involve distributed area sources. Instead of having earthquakes localized on individual faults, there's been some more recent work by Victoria Stevens and her colleagues at INSET, where they've been able to make a fault-based model for the main Himalayan thrust, but they don't include any of the faults in the upper plate in the Himalayan wedge itself. And these upper plate faults are, including the Western Nepal fault system, are not expected to produce anywhere near the magnitude of earthquakes that the main Himalayan thrust can produce. But they can still produce earthquakes in the magnitude 6 to high magnitude 7s, depending on fault connectivity and other factors. And because they're much closer to some of the population centers that are away from the Indian boundary, they can affect communities that are not as affected by earthquakes on the main Himalayan thrust itself. So in our preliminary model, that's still very much a work in progress, we've so far included 2 faults. We have the main Himalayan thrust, which we've represented with a slip rate of 20 millimeters a year. There's some variation here. This is just a kind of a test number. And we've given it a semi-characteristic magnitude frequency distribution. So this would allow it to rupture in earthquakes about 8.8, plus or minus some amount, and then as well as some smaller earthquakes around magnitude 6 itself. This is just sort of a number to put into the model right now for testing purposes. We'll do work later on once we have it all complete on better refining the magnitudes of that we would expect from the main Himalayan thrust and accounting for earthquakes more like the Gorkha earthquake. For earthquakes on the main Himalayan thrust, we are modeling the ground shaking at each location in our model using some relations that are called ground motion prediction equations. And these ground motion prediction equations take a rupture that we've put into our software that's an earthquake on an individual fault and predict what the strong ground motions would be at different points in the model. And so the set of equations we're using for the main Himalayan thrust are developed for subduction zones worldwide, and they have been shown to do a very good job of predicting the ground motions from the Gorka earthquake. So we think that they are appropriate, the most appropriate available ground motion relations for the main Himalayan thrust earthquakes. For the Western Nepal fault system, so far we've implemented the section of the fault from Talphi down through Jengla and the Dhaulagiri Southwest area. And this is basically what Andrew has been describing in the previous several slides. These are areas where we have, our research group has mapped and are working on characterization of slip rates and paleoseismology. I put in a preliminary slip rate of 3 millimeters a year on this fault. We don't have any numbers for this yet. This is just sort of an estimate because I needed to put in a number. And so when I talk about the numbers of ground shaking in the next several slides, please don't fixate on any of the individual numbers. We're just using sort of test data right now in this preliminary state. Once all of our geochronology comes back and we have better estimates for the slip rate, we'll be able to put the final numbers on this. We've given the Western Nepal fault system a sort of dextral normal kinematics. This is consistent with the kinematics that we've seen in the higher Himalayan segments of the Western Nepal fault system. I expect that as we continue the work to the southeast towards Tonson, it will change from being dextral normal to being dextral reverse as the system becomes more thrust oriented near the main boundary thrust. And for this area, we've used active shallow crust ground motion prediction equations. So these are relations that have high attenuation of seismic waves. They're suitable for areas of continental crust undergoing active tectonic deformation. I have not included background seismicity or distributed seismic sources in the model yet. We will get to this once we have the fault characterization done, which in our methods is the first step. And all the calculations I have are for bedrock. So this has a 760 meter per second shear wave velocity at 30 meters depth. And later on in the model, we will be able to include better site characterization. So including small sedimentary basins and things like that that may amplify ground motions. However, we don't expect that we think that most places in the model that we're going to study will have shear wave characteristics that are pretty similar to bedrock. These places are all well within the Himalaya, and there aren't these deep sedimentary basins where we would really expect a lot of amplification of ground motions. Okay, so here are some preliminary results from the PSHA, and for some reason it looks, unfortunately, like the colors did not come through in the color bar. So unfortunately, this is just a pretty slide that sort of looks like a sunset and doesn't have much quantitative information. But what we can see is that the high values, which are in yellow here, are located near the main frontal thrust where the Himalayan thrust reaches the surface. And these values become cooler colors, so more towards purple and then blue, as the Himalaya thrust becomes deeper underneath the higher Himalaya. And then here we can see the Western Nepal fault system from Talphi down through Dhaulagiri Southwest and Jengla segments. And this is Jufal here in the middle of it. And we can see that there are locally higher ground motions around Jufal that are related to the Western Nepal fault system. So the values here are calculated, the peak ground acceleration at an exceedance level of 10% in the next 50 years. And so the highest values, the values that are close to yellow, are a little bit over 1 G, that's, and G being 9.8 meters per second squared. And they decrease substantially towards Tibet, related only to slip on the main Himalayan thrust and Western Nepal fault system. If we include distributed seismicity and other fault systems, those values stay a little bit higher. But these are very high ground motions. You know, the area is very seismically active. And so that's motivating a lot of the work that we're doing. So here I have hazard curves for 4 cities, for Jufal in blue, Garahi in orange, Kathmandu in green, and Pokhara in red here. And so on the y-axis of this curve, we have peak ground acceleration. And on the x-axis, we have the probability of annual exceedance. So in the previous slide, we were looking at exceedance over 50 years. In this slide, it's the annual exceedance. So the values are quite a bit lower. And I don't want to concentrate on the numbers themselves because this work is very preliminary. But the point to make is that at the moderate annual exceedance levels, Jufal has the highest seismic hazard. It's higher than any of the other cities, even including Garahi, which is much closer to the main Himalayan, the shallow parts of the main Himalayan thrust at the main boundary and main frontal thrusts. And this is because of its proximity to these large faults. So Jufal and Tibrikot are literally adjacent to the Western Nepal fault system. And so we expect the seismic hazard there to be elevated, especially compared to other cities that are kind of at the same position at the base of the high Himalaya ranges. In those other cities, so Pokhara can serve as an example here, which is in red, seismic hazard is a bit lower than it is closer to the front of the main Himalayan thrust, because the main Himalayan thrust there is 15 or 20 kilometers below the surface, so there's a lot of attenuation in the wedge. And again, so these results may change as we increase our understanding of the slip rates, of the connectivity of different fault segments, the maximum magnitude of earthquakes that we would expect on these faults, and the frequency of earthquakes that we would understand from the paleoseismic data. So now I'm going to talk about work that Elaina Sutley has done on the characterizing the building stock of villages in the Himalaya. So so she was in this with us in the field for a little while and didn't spend as much time digging around in the rocks, but instead was looking at all of these villages. And so now we're going to go to the Talphi area that Andrew has shown about the neotectonics and talk about the buildings there. So the first objective of the fieldwork was looking at older residential buildings. And so these are some examples of older mud and stone-based structures. The one on the, they have a little bit of seismic reinforcement in terms of these some kind of horizontal wooden bands in the buildings themselves, but for the most part, they're not very seismically resilient buildings. They have roofs, for example, that are made of orthogonally laid layers of wood and stone. And these are, they're strong and resistant to rainfall and snowfall, but they are not good for seismic hazard because they're very heavy and they don't have much tensile strength. And so they cause the buildings to shake quite a bit more than they would otherwise. And also disaggregate under shaking. So some of the newer residential buildings have been built with knowledge of how the buildings respond. I think a lot of this has been due to both lessons learned in the Gorka earthquake, as well as just increase in investment in building stock in the area. So these are some buildings that have more wood frames. So these roofs have increased wood. There's wood lintel bands running across the buildings. And so we can see some of the construction associated with these and some measurements that are being taken for quantitative analysis. Again, so we can see that there's much more long wooden beams and wooden frames around doorways than are using in the past. And, these are lovingly crafted buildings made by locals who put a lot of care and have a lot of knowledge for regional building in the area. Okay. So we're also not only looking at residential buildings, but at buildings that serve in a larger, more civil capacity. So we have older school buildings that we've surveyed. And so these, again, are simply just you know, stones that are stacked and with mud holding them together. They have a little bit of wood involved in the door and window frames, but not a lot of through-going wooden infrastructure. Newer school buildings are a bit better. They have more wooden framing holding up the roofs and running throughout the buildings. And this was a health post that is in the finishing stages of construction. So it's very new and it has more wood involved. So we've also been doing quantitative surveys in addition to just characterization of the typologies of buildings. And so, for example, at the Talphi site, we have 1 school building and 159 residential buildings. And these will all be included into our quantitative analysis. So one of the interesting things about this work is particularly for us, I think all the Nepalis are pretty well aware of it all, but it's interesting for us to learn about how the building styles have changed and what the retrofitting styles are for buildings following the Gorkha earthquake. And so some of the new techniques that are used are more lintel banding, vertical reinforcements, as well as the horizontal lintel bands. For retrofitting, there's more stiffening of the roof to wall connections. There's wire mesh around a lot of the brick and mortar construction. There's bamboo reinforcements of a lot of walls as well. And so these are relatively inexpensive techniques that can really help stabilize buildings during ground shaking. So the work that's in progress by Elaina and her students are making very high quality, high resolution, finite element models of these individual building typologies based on our field surveys. And as this work progresses, we're going to take the ground shaking predicted by individual earthquakes and subject the buildings to these ground motions to understand how different earthquakes on the Western Nepal fault system and on the main Himalayan thrust are going to damage all of the different types of buildings that we've seen in our surveys. And this will give us a very high accuracy assessment of the probabilities of losses associated with different tectonic constructions or configurations on the faults in Western Nepal. And again, so this work is ongoing. We've gotten 1 field season out of the way. We were not able to get the one in 2020 for the same reasons that everyone else has had so many problems during this year. But we're very excited to be back and work with you all on this interesting work. So I'd like to thank all my collaborators, both the ones that presented, Andrew and Mike, as well as the ones that did not and were with us, as well as our field support from Bhim Chand and his company, and our academic colleagues, including Basanta, and I would like to thank you all for watching.
Thank you. Thank you, Mike, Andrew, and Richard, for your combined and wonderful presentation. Can you just close your slide, Andrew? Yes, perfect. So yeah, it's very wonderful that you have started this active seismotectonics and then, you know, try to show the field evidences of this offset, and then, you know, to talk about this probabilistic seismic hazard assessment and how mud mortar buildings are there. And this area particularly is very, very important because, you know, as you know, the Jumla is one of the places in Nepal that people, you know, have their traditional knowledge on seismic, you know, use of, you know, before this, you know, building code is started in Nepal, they have started these lentil bands and others. So this place considered one of the, you know, best traditional knowledge on these things, and what you have rightly mentioned and showed some of the photographs. And I hope, we'll work on this area more on how to, you know, analyze on this. I don't know how far we can go to define the fragility curve of these buildings and others, but we'll try to do that. Definitely, maybe you will explain a little bit later on if there are some questions. So I would like to request our participant, please post your question in Facebook live streaming and here in Zoom chat box. So I will start from the Zoom chat box. Okay, so this is one fundamental question from Devika Kese, asking why there is absence of major earthquake history in Western Nepal compared to eastern part. Can you address, maybe Mike?
Well, Western Nepal falls in an area that's called the Himalayan Seismic Gap, or Central Himalayan Seismic Gap. It hasn't had a great earthquake since the 1505 AD earthquake that ruptured both the main frontal thrust, and actually we think we have found evidence that it may have ruptured the Western Nepal fault system. Now, the nominal recurrence interval, if you want to use that for these great earthquakes, is sort of varies at a low end from 500 up to even over 1,000 years. And so we're sort of at that, many people might say 750 years. So we're sort of been long overdue for a great earthquake in Western Nepal. But you're right, it has been a lack of great earthquakes, and that's why we sort of define it as this seismic gap.
Yeah, thanks, Mike. Another question from Dave Morgan to Richard Staden. So which GMP models are being considered for subduction zone and active shallow crust? Richard, can you address that one?
Yeah, I remember that I used just a preliminary one for this model that aren't the final ones because we haven't done a lot of selection. But I used Chow and Young's 2008 for the active shallow crust, and I think that I did the work a while ago and forgot the details, but I believe I used an Atkinson and Bohr model for the subduction zone, but I could be wrong about that.
Thank you, Richard. So another question from Sanjay Jha. So he's asking the preliminary hazard curve shows maximum PGA of 0.1 GUL only. Is this curve specified to a particular fault? If yes, it appears that this fault will not create a significant damage compared to the fault which can result in a max PGA of 0.2 to 0.5 or more. What's your observation on that? Maybe Richard, you can address that.
Like I said during the talk, the work is pretty preliminary, and so I don't want to comment too much on individual numbers. And I don't want to talk a lot about the final hazard curves until we're including all of the sources. So right now it's just a way of showing some of the expected outputs of the analysis, but I don't want to. The analysis is not final and it's not complete.
Okay, thank you. So another question from our colleague Diliran Thapa, because he has done lots of work on this PSHA. So he's asking, how do you constrain the geometry of main Himalayan thrust for seismic source? And another hypothetical scenario, what is the view on magnitude +9 earthquakes in this collided zone? Richard.
So I'm using a constant dip on the main Himalayan thrust that comes from the work by Victoria Stevens and Surya Thresha at INSET and with John Philippe of Walk and previous collaborators on that. Once the work by Soyafon and Mike Murphy is, well, it has been recently finalized, but in the next couple of years, I will start using their more detailed geometry of the main Himalayan thrust, including the presence of frontal and lateral ramps, to come up with a more accurate representation of the main Himalayan thrust, and ideally be able to assess earthquake segmentation on the main Himalayan thrust as well. Our project is funded mostly to study the Western Nepal fault system, so I'm not going to devote most of the time to the main Himalayan thrust. However, particularly if we can demonstrate over the course of our project that there are strong linkages between earthquakes and faults in the Western Nepal fault system and the geometry of the ramps and the main Himalayan thrust, then I will include more segmentation on it. As far as magnitude 9s go on the main Himalayan thrust, there's I think that we have to consider that possibility. It may be that there are persistent rupture barriers in the form of ramps and other, potentially frictional barriers on the main Himalayan thrust, but the paleoseismic evidence shows that there are extremely high displacement events that occur on the main Himalayan thrust. So these are 10, 20 meters of displacement, and those can only happen in great earthquakes. So 8.5 to potentially 9.2 earthquakes. Because we're going to be doing a probabilistic analysis, we can include those earthquakes with some possibility, but we don't have to say, okay, this kind of earthquake will happen every instance. And so once we have the Western Nepal fault system better characterized, we will start more quantitatively evaluating the magnitudes of the main Himalayan thrust. But others are working on that as well. And that is the focus of their work, whereas ours is the Western Nepal fault system. So I will lean heavily on work that other people are doing.
Okay, thank you. So another question from Mary. Actually, I wanted to ask that question, but she raised that's very pertinent question. The question is, do you see evidence for seismicity that aligns with WNFS that is deeper than main Himalayan thrust? I ask because we are working on segmenting faults, cross faults in Eastern Nepal that have some deep seismicity and may relate to inherited basement structures. Richard?
I haven't looked into that at all. I know Andrew Hoxie has looked into the microseismicity a little bit.
Okay, yeah, please. Sorry, Andrew.
Yeah, so the microseismicity signal, as Mike Murphy has pointed out, has a single band in central Nepal, and then it bifurcates as you move west. And so that bifurcation is co-located approximately with the trace of the West Nepal fault system. We're still in the process of basically drawing profiles across the system to see how they align with depth, but generally you see the microseismicity right at the base of those ramps.
Okay, so another question, maybe Andrew can answer that, from Camille Qureshi. So how did you calculate the thickness of the thrust wedge?
Oh, I'll comment on that.
Okay, Michael, please. Michael.
Yeah, so, FAN put together all these cross sections. In fact, that model, I'm sure there's many people that are watching right now in which there are cross sections included. So thank you everyone for contributing to this 3D model. What we do is we've just incorporated this into Move. We use a combination of ArcGIS and 3D Move to build that three-dimensional model from the 2D cross sections. And what you're looking at is simply the thickness of the uppermost shear zone called the South Tibetan Detachment down to the MHT. And in fact, in that model, we do use the Stevens and Avlak 2015 MHT grid. Everyone can go download in their supplementary files. And so that's the form bottom, and the STD from previously published cross-section gets us the top. And so that's what we're thinking about for the thickness.
Okay, thanks, Mike, for your clarification. So another question from Sarad Wagle, asking, since the study is focused on Western Nepal, do you have a plan to measure the shear wave velocity in different sites, or use the standard 760 meter per second for bedrock value? Any of you can address?
It depends on how much time we have to work on the site characterization. That's not the focus of our study, but I think that we may make a sort of use VS30 from slope approximations in some of the areas to kind of come up with statistically derived VS30 profiles or VS30 values. But right now we're focusing on the fault characterization and the seismic source characterization more than the site characterization. And just to reinforce, none of these are going to be measured values unless they're our team is not making measurements of the shear wave velocities. So we will rely on work that's done in the literature for that component.
Okay, thank you. Hopefully we'll get some more question for 5 or 10 minutes. In between, I have some, observation that might be interesting for our participant to explain a little bit. Just maybe Mike or others can explain. So just a couple of months back, John Waldron and others, they have published a paper on active fault, south of the main frontal thrust, 30-40 kilometers south of the main frontal thrust, based on this, deep logging of this Terai Indo-Gangetic plain from the Schlumbergers. And so, this is still going, the discussion is going on how these active faults, are, actually associated with this new kind of, developed or not developed, the research have produced that result. So do you have any comment on that, how these new findings can be related with your study, or maybe because Mike, at a point, Mike showed the cross-section of the two Himalayan cross-section. So do you have any comment on that, Mike, or some other colleague?
I'll make a couple comments, and maybe it relates to the propagation of the deformation. We're working on a model now to sort of try to explain how this Western Nepal fault system propagates with the thrust front. You can see that if you read many of our papers, we call upon oblique convergence to drive these splay faults, drive the strain partitioning. This represents strain partitioning within the thrust wedge. We know that thrust wedge evolves and gets longer with time. If we go forward in time, we know that MFT, or the frontal part of the deformation front, will propagate, and so will the splay fault. If you looked at when Andrew was showing the branch line, the exposed branch line between the splay fault and the MFT, that's a time transgressive point. It wasn't always there. 15 million years ago, that point was way back up in the Himalayas, and has simply gotten longer. The splay fault and branch line have therefore probably propagated with the deformation front. I'll also just comment on that 3D model. You can see that the kinematics are really different off to the west than in the central part. And we think that's because of the increased oblique component to the thrust belt, as Richard Styron published and others in 2011, where we were looking at the arc parallel velocities. You can in central Nepal, right at Everest, things aren't going laterally at all. They're not moving laterally, but there's a strong gradient of that velocity as you move to the west, which we think starts to stretch and thin the thrust wedge as you move into northwest Himalaya. And you can sort of see that difference between those two cross sections. What you saw in those two cross sections is that the crystalline, or the Himalayan crystalline core, was very thin, while in the central or western Nepal, and as you go to the east, it gets really thick. And so we think it's a lot of this oblique convergence and the basal shear traction that's then taking over and translating and stretching, elongating the thrust wedge as you move to the west.
Yes, thank you. And another, after this Gorkha earthquake 2015, this year we have been receiving, lots of landslides, and the people are talking about whether these landslides are only related with this rainfall or this the earthquake affected areas, the coupling of the rainfall and then the landslides. And then people are again talking about, oh no, that's not true, because in the Western Nepal, the Gorkha earthquake didn't affect anything, but we have landslides. So, because you have shown some of these field photos, so do you see still there are, in the recent time, this active tectonics going on that area? So that we are receiving landslides in that region. Do you have any comments or observation on that?
I have an observation, and that's from walking from Jufal or Jumla all the way to Jufal. There's all these brand new road systems that are being put in. They're building these dirt roads everywhere, and every road is just collapsing. There's landslides. I think the roads are triggering the landslides, at least many of them in that area. I don't know how many of you guys have been there recently, but man, the effort at building roads is quite prolific. And these are roads embedded within, highly foliated, fractured phyllitic rocks and so forth. They swell up, with rain. But obviously there is, as we've shown you, there's active deformation.
That's good. So another observation, because I'm not good on this probabilistic seismic hazard assessment, but when I saw the curve prepared by Richard, and the curve shows that it's quite symmetrical for Pokhara and Kathmandu, which is different for Jufal and other city. And then, after the 2015 Gorkha earthquake, we were amazed, and still we don't know the reason that how this seismic wave, the energy propagated towards the eastern direction from the Gorkha epicenter towards the eastern direction, not to the western direction. So people are still talking about there should be some north-south trending fault. So does, if this fault is there, does it affect on your model, or you didn't consider that fault in your model, Richard?
I didn't consider it in the model, but I think that there are, based on interpretation of the kind of tectonic configuration of oblique convergence and the geodesy, the GPS velocity field, I think that there have to be more north striking faults in the Himalayan wedge, east of the Western Nepal fault system. So maybe near Pokhara, there's some around Kathmandu, and some have been mapped that are in some of the river valleys. I can't remember the names of anything. And then working all the way east towards the border with India and in Sikkim. And so I think that there's evidence that those faults are slipping a couple millimeters a year, and that there's active east-west extension of the Himalaya there. It's hard to see relative to the signs in the west, where you have these dramatic valleys like the Takalagraben and Mustang, and but I think that there is some evidence for it. What I don't understand is to what degree that would affect the propagation of seismic waves or the directivity of seismic energy. I don't know very much. That's outside of my field of expertise, and I think it would be very interesting to study. And so hopefully someone who's a real seismologist can address that question, because I'm not. I'm more of a structural geologist. So,
any other has a comment on that?
I'll just comment that, when you look at the nominal rupture areas for historic earthquakes, they seem to never be able to, there's some barrier right there at Gurla Mandada and Takala. They don't seem to cross that region So like, we would suggest, as others have, is there's probably some ramp system. I know Laurent Bollinger has called upon the Gorla-Minada, a north-south, some sort of rupture barrier. After, you can see our ramp model, and we would call that a lateral ramp. But it looks like there may be another one over at HETAUDA.
Mm-hmm. Yeah, thanks. So I'll take one, probably one last question. And then, okay. So from Ratnamani Gupta asking, why VS30 only? Why not VS20, 40, or so on and on?
Those are inputs into I think our ground motion prediction equations right now only take VS30, the ones that I'm using, but I'm not the expert on the ground motion stuff. And so I'll have to get some help from my colleagues at GEM if we want to use more sophisticated shear wave velocity profiles. But yeah, I'm not the expert in that. But I know that the VS30 is one of the standard inputs into the ground motion prediction equations. The reasons for that, I don't know. I don't know the history of that. So.
Okay, so I'll take one question from Facebook chat. I don't know, it's totally related to your study or not, but Sandeep Pradhan is asking, have any research on mass movement recorded in Nepal due to internal seismic activity conducted in Nepal through time-lapse study? Mike?
I didn't quite understand that one.
So the question is, are there any research on mass movement recorded in Nepal due to internal seismic activities through the time-lapse?
Oh, like monitoring continuously a particular region?
Yeah, due to the internal seismic activities.
Yeah. I'm not aware of too much of those studies. I have enjoyed some of these INSAR studies in central Nepal that have been looking at changes over time, particularly right there at the south end of Takala, where it looks like there's a new ramp that's forming. It was a paper published in 2012 by Grandin. What I'm not familiar with is if, like a colleague of mine, if they're doing any monitoring of large landslides. I'm sure they are, sort of looking at the mass movement in that way. But no, I'm not that familiar with that.
Yeah, I mean, I can just elaborate somehow on that. Most of all people who are working in natural hazards are monitoring landslides from the geomorphological perspective, the mass movement and slope processes. But due to the internal seismic activities, there are very few people are working on, like rightly Mike mentioned about these INSAR technologies. But what I've seen in Kathmandu Valley, they have doing some research on subsidence analysis. Maybe after Gorkha earthquake, people are working on the deformation analysis by using the INSAR and others. But for the large scale mass movement and landslides from the internal seismic activities, still we have to go along. So it's still in primitive stage of that research. I think that's all the question. Let me see once again. Okay, so now I would like to invite if you have any remarks, Mike Tyler, do you want to express any views on from you? Sorry, you can unmute by yourself.
You have to unmute yourself.
Yeah, I think I figured it out. Yeah, I just wanted to say thank you for inviting the team to give a talk today. As far as the neotectonics, I think there's, as Andrew showed in his slides, there's still a lot to be done. There's so many faults that are unknown in Nepal. And I think that we're just a small group of geologists and geomorphologists and paleoseismologists that are doing work in one spot in Nepal. Based on what I've seen, there's so much more to do. And I think that when you look at Richard's preliminary PSHA model, there's basically just two faults on there, one really big one and one really small one. And so I think it's, to say that that's an accurate representation for Nepal, I think that's a bit of a stretch. And so I just think it would be really great if we could get more community involvement and more boots on the ground and map some more faults, because we're still in very preliminary stages and there's so much more work to be done.
Thanks. Yeah. Thanks, Mike. Yeah, of course, you know, Himalaya is a natural laboratory and it's a complex structures, especially when you talk about the paleoseismology and active tectonics, or, you know, structural analysis or metamorphism. You know, when you look at the Himalayas, it's simply a complex thing. So we have to work on these things together to identify at least some of these features on that area. So I see the scene. Bemis, do you have anything to share?
I'd like to amplify Mike Taylor's comments, you know, just about how, you know, you look in detail and you look for the clues for what, you know, what we learn about what active faults look like. And we see more and more signals as we, you know, as our remote sensing technology gets better, we get a better view of the Earth, and more of these signals start showing up. And I think we're going to see quite a few more bits of active faults even outside of our study area come into clear focus in the coming years. And you know, it's been quite exciting. You know, this was my first time doing paleoseismology in the Himalaya, and you know, it was a new challenge relative to working in a place like Alaska where there's not a whole lot of people. And you know, we need, you know, for paleoseismology, we need to look at that skin of the Earth. And you know, there's been a lot of ground modification from agricultural activities, and so there's you know, I think, but we're finding some good clues, and I think we can complement. There's a recent study where they did some paleoturbidite studies in a lake and Lake Rara, and those are really valuable in terms of like the strong shaping in a region, you know. But we need we're trying to do this on fault paleoseismology so we can actually place an individual earthquake on a specific fault, and so. It's nice to have some parallel studies in the region that we will complement this work that's going on.
Thanks, Sam. It's a wonderful addition about these things. You know, of course, this kind of the data what you have mentioned about this lake drilling project from Rara, or when you look about these seismites in these lake layers, and then other. It's quite important. Moreover, we have to understand this thin skin tectonics of the Himalayas to understand better results and others. So let me see here. Okay, yeah.
I want to add too, you know, 10 years ago, Taylor and I were sitting up there, like in the upper parts of Dolpa, and we found these like beautiful like lakes, these lake terraces.
Oh, yeah.
Really a lot of other features up there that need to be explored.
Yeah, and I was going to say there's a lot of landslides up there that form those lakes, and so I think there's a very rich, not only a climate record from those lake deposits, but just kind of a paleo landslide history that is virtually untapped. Nobody has looked at that, to my knowledge, in great detail. So that right there is a beautiful archive that needs to be explored. The other thing I was going to say with regard to your comment about some of the faults that are growing, that are active south of the main frontal thrust, I think one also untapped field of study that could be utilized is LiDAR technology. And to my knowledge, I'm not aware of any extensive LiDAR data sets in Nepal, but I would bet if there was an extensive coverage of LiDAR, you would be able to have there would be so many faults that you would identify within that data, is my guess. And so that would be something worth looking into as well.
Yeah, I mean, in my knowledge, I think we have some airborne LiDAR image along the main frontal thrust from east to west from Singapore study group in Global Observatory. But as a whole, you know, Himalayan region, particularly which you mentioned the area, I think we didn't have that area. And the LiDAR techniques is quite important because that we use terrestrial LiDAR scanning we use in our this study in Tibrikot region after 2015 earthquake, and we published a paper in Science in 2018 about whether the large scale one event, for example, CLOP, is really important to change the landscape, or this every year monsoon and others. So it's quite interesting to explore this terrestrial LiDAR scanning and other things. Thanks, Mike, for putting this forward. And yeah, it's very interesting discussion, and I would like to thank you all. And like Mike Murphy explained, that we'll have next session next year about field route, and we'll run a short course about this thing. And of course, our Nepalese participant and other interested researchers will inform during that time. So having said that, before I hand over to Suraj Gautam, do you want to say any final remarks, Mike Murphy?
Other than we have just fully enjoyed our experiences in Nepal. It's not only spectacular geology, but what makes it so great is such a wonderful place to visit, the people, the food. It's great. Thanks, Basant.
Yeah, thanks, Mike. So again, thanks, Suraj, for providing me opportunity to moderate our esteemed colleague from around the globe. And I would like to thank our participants for your very, very in-depth and interesting questions. We have to do work to identify and to explain all these answers of your questions, and hopefully we'll be able to address some of them in coming years, at the end of our project, not all, but hopefully some. And thank you once again. And now, Suraj, over to you.
Thank you so much, Dr. Basanta, for the excellent moderation, as always. We'd like to thank Professor Dr. Michael Murphy, Professor Dr. Michael Taylor, Dr. Sin Bemis, Dr. Richard Styron, and Andrew for the excellent remarks on the using convergence research to connect 3D architecture of the Himalayan thrust wedge to the seismic hazard and risks in Western Nepal. It is really good to see our presenters working actively in the Nepalese Himalayas, and the Q&A session was also really interesting with and as we had a lot of quality questions, and we tried to address all of the questions from our Facebook page live streaming and also from our Zoom chat box. In case you have any further queries, you can please write to us at info@inhrr.org. I'd also like to convey my big thanks to all of our organizing team, speakers, session moderators, our distinguished guests, and participants for participating in this session. The session was really informative and interactive. We'll be sharing the recorded session on our YouTube channel, and the links will be forwarded to all of our registered email address. And we also have a scheduled webinar episode on geoscience for sustainable development for this September 20, which I would like to share here. The topic is regarding the importance of engineering geoscience for sustainable infrastructure development, which will be presented by Mr. Sam Gimire, who is a principal engineering geologist working at NSW Australia. So we'd like to warmly welcome you all to join this episode as well. So we'd like to request all of our participants to please fill up the feedback survey form as well. And our participants can also suggest us some potential future webinar topics, and we'll try to address your request. So we'd also like to mention that Institute of Himalayan Risk Reduction will be more than happy to collaborate and organize this kind of relevant webinars in the days to come. So with this, I would like to sign off from our session for today. Thank you once again. Stay safe. Namaste.
Namaste. Bye-bye.
Namaste.
Thank you, everyone.
Thank you.